Hello everybody. In this video we're going to do section 7.5, which is a strategy for integration. Let's jump right in. So far we've seen individual techniques that have been applied in each section. For example, in section 4.5 we use substitution usually. 7.1 it was integration by parts. 7.4 it was partial fractions. In this section, we're going to present integrals more or less randomly. And the challenge, the skill builder, is to recognize which technique or formula you need to use to complete the integral. And there's going to be guidelines, but no hard and fast rules as to which method applies. So the guidelines are outlined on the next few slides. And roughly it goes like this. You want to memorize your basic integrals if you haven't done it yet. And then there's going to be a 4-step process that you want to proceed in that order to evaluate integrals. So most of these you probably already have memorized. Even if you don't, some of them can be derived. For example, number 19 on the next slide, you can do partial fractions. And formula 20, you could do trig substitution. So this is what we just call the 20 basic integrals. Many of these we've proved in class. So in Calc 1, you proved this one. But this one, maybe you did it in Calc 1, maybe you did it again in Calc 2. Right? So just in the notes so far are proofs for this, just in Calc 2. This and this, and then all of these. So about half of these we proved in Calc 2 already. About half of them were from Calc 1. And as you can see, 19 and 20 have asterisks because those are ones that you can derive using partial fractions or trig substitution. You don't have to memorize them. You could work them out on your own. All right, so our first step, if you want to try to figure out how to integrate a random function, would be simplify first if you can. It doesn't always come up, but if you miss it, you could do a lot of extra work. So here's a good example. Over here, this looks like a U substitution, but if you distribute, it turns into just a polynomial. And polynomials, we can use the power rule. So if you can simplify first, you definitely want to do that first. It'll save you the most time. So that's step 1. Simplify if you can. Step 2. U substitutions are always the first step given the choice because they're relatively fast, as you know, compared to the stuff you've seen in Chapter 7. So here, we call this an obvious substitution because x looks like the derivative of 1 plus x squared. And when you set up the U substitution, you see that it is exactly 1/2 of the derivative, right? So it's just 1/2 1 over u du, and that's an easy integral to do, right? It's just the natural log of 1 plus x squared plus c. So first two, pretty straightforward stuff, Calc 1 level stuff. If these don't work, steps 1 and 2 don't work, then you're forced to start making some choices. And the choices are based on the form. So if you see trig functions multiplied together, you want to follow the techniques from section 7.2. And you want to use identities and manipulations and things like that. If you see rational functions, if so, that's polynomial divided by polynomial, use partial fractions from 7.4. If you see combinations of polynomials, exponentials, and trig functions, as we've seen, that's integration by parts. Integration by parts is good at doing lots of different kinds of integrals, but because it's a very long process, you don't want to use it unless the other techniques don't work. And radicals, right? We saw how to deal with radicals in section 7.3. Anything of these forms is a trig substitution. And you could use a rationalizing substitution if you have just the nth root of something. Just try that as the substitution. So step 3 is based on how the integral looks. And all of these look very different. So simplify if you can, use substitution if you can, and then choose the form if those don't work. And it turns out that even if you've tried all these steps, it still might not work. You might have to go back and try again. Maybe you missed something the first time around. There's really only 2 methods of integration, substitution and parts. So where does this come from? Why is it true that there's only 2 kinds of integration? Well, think about derivatives, right? Integration is derivatives backwards. Substitution comes from the chain rule. Parts comes from either the product rule or the quotient rule. Those are really the only complicated rules that you have for derivatives, is the quotient rule, product rule, and the chain rule. So when we're working backwards, those are really, the main ones that we think would come from a derivative when we're taking it the other way. So go back and try substitution again. Even if nothing is obvious, try something not obvious. Just start messing around and see what happens. You're not going to break math, but you might manipulate something and see, oh, there's the answer I was looking for. Try parts again. Even if the integral doesn't have the form that you'd think of as parts, we've seen that it works on arctan x, arcsine x, and natural log of x. So we know parts works in other situations. Maybe give it a try. And if substitution and parts don't look right, you might have to rationalize the integrand, or use trig identities and move stuff around. So that's sort of the basic strategy for the try again. Maybe you overlooked something as substitution. Maybe it didn't look like it should use integration by parts. Give it a try. Try to rationalize. Try to simplify. Try to factor. Anything like that. Also, you can relate your current problem you're working on to a previous problem. So any formula we've worked out can be used to solve a new problem. For example, if we use this identity, tangent squared is secant squared minus 1, then we can turn this integral into those 2. And we have formulas for secant cubed and secant. Right? We actually proved both of those in section 7.2. And they're just formulas. So if you went through the proofs, you can just pop the formulas in. You don't have to work through the problem again. If you know the integral of secant cubed is 1/2 secant tangent x plus natural log of the absolute value of secant x plus tangent x, then go ahead and write it down. And of course, if you were doing this problem, if this was a problem I put on a test, you would want to simplify it. So that's the answer at the bottom. All right, so that's another thing you can do, right? You can use results proven in previous problems, or maybe there's something you just remember from a homework and you know the integral. Go ahead and try it. Or, of course, you can always combine methods together. So maybe you try one technique and then it advances you somewhat through the problem and then you get stuck and you have to use a different technique. Right? We've seen that before, right? Back in section 7.4, example 4, the integral of 1 over 1 plus x cubed. Remember, it had all of these steps and we needed to try lots of different things along the way. So we've already seen that and it can happen again. So that's it. Those are your integration strategies. Simplify first, which also includes simplify as you go, because some of these multi-step problems, they might open up pretty big and you want to keep them sort of condensed because you might have to keep doing integrals. So yeah, simplify first, use substitution, classify by form. If those don't work, try it again. And this time, look for non-obvious substitutions. Look for integration by parts when you don't know if you need to use it. Combine methods, try rationalizing, and use any formulas that you might already know. All right, so let's see an example. So here are 4 problems that, you know, when you saw these before in either chapter 7 or earlier, you were basically told what technique to use because of the section you were in. Now it's up to you to figure out what technique to use. And I'm not doing full solutions on all of these. If you're not following the algebra or the calculus, make sure you're filling it in on your own. Trying to keep this video under 35 minutes. We'll see if I can do it. All right, so let's jump into the first one. You would try simplifying. No way to simplify it. And you want to look for an obvious substitution. So here we have a function to a power, so we want to use the power rule. We use the power rule when it's like u to a power, like u to the n. So that tells us that u should just be the inside function. Oh, that should be plus, sorry. It doesn't matter though because it goes away when you take the derivative, so that should be a plus. So u to a power. Oh, sorry, wrong button. Let's try it again. Yeah, so u is just the inside here, 3x plus 1. Du is 3 dx. Solve for dx. Plug everything back in. So we just have u to the radical 2. Dx is 1/3 du. And then we have to change the bounds of integration by plugging them into here, 3x plus 1. So 3 times 0 plus 1 is 1. 3 times 1 plus 1 is 4. Here we have the power rule. When we do the integral, you're going to add 1 to the power and divide by the new power. So we just get u to the radical 2 plus 1. The 1/3 comes to the front. And I'm going to pull this to the front too, so I just wrote it as 1 over. Plug in 4, plug in 1, and you're done. So you just get 4 to the radical 2 plus 1, minus 1 to the radical 2 plus 1, which is just 1, and then all the constants were pulled to the front. So, it might look pretty ugly, but this is the way to do it. Relatively straightforward u substitution problem. All right, let's do the next one. So you might be looking for a way to simplify. You can't. The bottom might factor, but there's no common factors to take out. There's no conjugates to have. There's no simplifications to be done that are obvious. And there's no obvious substitution, right? The derivative of t to the 4th is 4t cubed. I don't have a t cubed here, so you don't want to mess around with that. So you're thinking, you move to the form. This is polynomial over polynomial. This is a rational function. Maybe partial fractions. So the first step of partial fractions is to completely factor the denominator. So we can do that. And what you get when you factor this is some really awful stuff. And if you remember doing partial fractions in 7.4, you remember that you want these denominators to look really nice, because when you do the partial fractions, you have to get a common denominator on all this stuff. So you can see that if we were to do partial fractions, this would not work out well. So even though it is possible to solve it with partial fractions, I don't think it's a good move, because this thing's going to chain out really, really big, and it's going to be almost impossible not to make a simple algebra step doing that much work. And if you want to try it, go ahead. I'm not going to stop you. But let's choose another path. Even though we can do it with partial fractions, maybe there's a better way. So let's look for non-obvious substitutions, because this is not integration by parts, so it has to be a substitution. So you might just be kicking around looking at it, and you might notice this situation. And this suggests that if we make t squared the substitution, maybe we can get somewhere with it. Right? So u equals t squared. So du is 2t dt, so 1/2 du is t dt. That's good. We have t dt. We can plug in 1/2 du, and we're going to have 1 over u squared plus 1 times 1/2 du. And then, maybe you didn't see it at the beginning of the problem, but now it should jump out. This is just arctan of u. And believe it or not, we're done with the problem. So this is what we would call a non-obvious substitution. But it is a substitution nonetheless because we have arctan, arcsine, and arcsecant. Those integrals pop up so much. All right, well, that one wasn't too bad. Good thing we didn't do partial fractions on it. All right, what about this? We can't simplify it because there's nothing to cancel. So we look for an obvious substitution. So the obvious substitution would be arctan of y. It's the only inside function. And you look for the derivative of arctan of y. Well, we have 1 over 1 plus y squared is the derivative. And if you just plug all these pieces in, it turns out that when you do the u substitution, you just get e to the u. Du actually takes care of all of the rest of this. So this, and that are all part of du. Now we just have to change the bounds. So arctan of -1, hopefully you know what it is. Arctan of 1, hopefully you know what that is. That's negative pi over 4 and pi over 4. You will absolutely have to know those on a test. And we're done. So problems that look really complicated can turn out to not be very complicated. Like this one. All right, one more in this first part to go. Really no way to simplify it. And there definitely is no obvious substitution. I don't see the derivative of anything out there. So now we have to look at the form. I don't see anything that looks like any of the forms, but we can rewrite this to get it to look like one, right? So even though the denominator is presented as exponents, if we write it as radicals, now it has the form of a trig substitution. Specifically, x equals sine theta. So if we do this substitution with dx cosine theta d theta, plug everything in, it sure looks like it's going to work. Remember, these trig functions, once you get them into the integrals, you have to do a lot of manipulation. So you don't know ahead of time if it's a good integral to do until you get going on it. And it turns out that you can fill in the algebra steps. It simplifies to this, then this, and now it's looking pretty promising because we know what that is. That's just tangent theta plus c. But we're not allowed to stop. Our original integral was in x, so I have to convert this back to x, which means I have to draw the triangle for x equals sine theta. When you draw the triangle and you read the tangent off of that, of the angle theta, you get, in fact, x over square root of 1 minus x squared plus c. And it turns out this one's really easy to check your answer. Just do the quotient rule and you'll get this back. So it's pretty neat. So this was a pretty straightforward trig substitution problem, but it didn't really look like one at first. So we just had to kind of fiddle with it a little bit. And that's the way a lot of these go in this section. You're going to have to be really organized when you solve these problems. You're going to totally have to have the first 4 sections of Chapter 7 completely mastered. And memorize what you can, because you're not told what techniques to use. And so that can present problems. All right, now let's keep going. So in this example, we're really not as interested in working all the way through these problems as can we identify the form? Is it a substitution? Is it integration by parts, etc. And then I put the answers on the next slide just in case you want to use these to practice. Many of these problems are straight from your homework, or something like it is straight from your homework. So you can never get too much practice. All right, so let's just start on the next slide. Let's look at A, B, and C right off the bat here. So look at the form. There's no way to really easily simplify it. I mean, you could factor a 2z plus 1 out of here, but you can also do that with long division. So it's looking like this is going to be partial fractions, polynomial divided by polynomial. And if you actually go through it and do the work, you will get 12 plus natural log of 9. So go ahead and try that problem on your own using partial fractions and make sure you can get this answer. Alrighty, let's look at the next one. This just looks all kinds of ugly. The only thing we have going for us is that there's a lot of natural log of x here, and there's an x down here. The derivative of natural log of x is 1 over x. So this looks like it's going to be a u substitution involving natural log of x. So what you want to do is pick the largest inside function that has a natural log of x, which would be 1 plus natural log of x squared. And it turns out if you do that substitution, you in fact will get the right answer, which is square root of 1 plus ln of x squared. So starts off pretty gross and ends up pretty decent. So give that one a try as well. Make sure you can do it. But also understand why we chose the substitution based on the way it looks. All right, part C here. So it's a definite integral from -1 to 1 with this whole mess of functions. Well, it turns out that the only way to do a polynomial times a trig function is with integration by parts. You don't want to mess around with integration by parts where this is your dv, because then you'd have to do this integral. So this is just looking horrible. So, and integration by parts is the technique that usually works when other techniques don't, because this definitely is not a substitution. So we might have to get really clever here. One thing you might notice is that this function is even, this is even, this is even, and this is odd. Even times odd is odd. Even plus even is even. Odd divided by even is odd, which makes this an odd function. And the integral of an odd function from -a to a is 0. So the answer is 0. This is based on techniques we saw back in section 4.5. First thing we studied in the class. You cannot do this integral. It's too hard. And it might not even be able to be done, as we'll discuss here at the end of the video. But using things like even and odd functions tells you that this is in fact 0 because of properties of even and odd functions that we saw. So if you forgot that stuff, it was only 4 weeks ago, go review it. And hopefully you can get that stuff under control. So there you go. So it's 0. What do you know? All right, the last one was sine of radical AT. So we called this a rationalizing substitution. There's no obvious substitution here, so we really were forced to pretty much make that u and just see what happens. But the trick we can use is you're allowed to square both sides. That gets rid of the radical, and when we take the differential, the radical disappears. Because if you take the differential here, you're going to be stuck with a chain rule and a radical in a denominator, which we don't have over here, so we can't do that. So the trick here is, in fact, set u equal to radical at, square both sides, then take the differential. And now we can just divide this by a and substitute everything in. And it turns out you just get this, and it works out real nice. Right, so this is 2ua du is dt, so 2ua du. And then this is sine u. Now what we've done is it put a u in front of my sine u here. And this is a product of a polynomial and a trig function, which is integration by parts. And it turns out you finish it up using integration by parts. So give this problem a try. And make sure you understand why you're using the rationalizing substitution, why you're squaring both sides before you do the du. It's a good trick. You will see this again. And then make sure you can do the integration by parts to solve the problem at the end. And then you have to back substitute u, and then you have to back substitute at. So those are just a few of the things that you're going to have to do in this section and possibly on an exam. Will our strategy for integration enable us to find the integral of every continuous function? So can we use this strategy to evaluate e to the x squared dx? So there's good news and there's bad news. The bad news is that we can't, at least not in terms of the functions that we're familiar with. So it turns out that there are lots and lots of functions that we can't easily find integrals. The ones that we can easily find integrals are called elementary functions. But not every elementary function has an elementary function integral. So all of these are elementary functions. And this is everything you've ever seen in a math class so far has been an elementary function. But some integrals are not elementary functions. This is one of them. It just can't be written any way as finite combinations of these. It can only be written as infinite combinations of some of these things. So if we have an elementary function, the derivative has to be an elementary function, but the integral doesn't need to be one, as I said earlier. So if we're looking at e to the x squared, it's continuous, so the integral definitely exists. And if we define the function by fundamental theorem of calculus, take the derivative of both sides, then f prime, so capital F prime, will be e to the x squared, which means that there is some function, capital F, that is the integral. So it exists somewhere in the function universe. We just can't write it using the techniques and the types of integrals that we've done so far. So the good news is that any function you see on a homework or on an exam, you will be able to do. And those fall into a relatively small class of functions, believe it or not. And you will see more about those functions in the next section, where we're going to use technology and tables to just sort of brute force integrate lots of functions without going through a lot of the calculus. We've already proven a lot of the calculus, but I'm going to show you how to do it using tables and technology in the next section. As to this integral here, the integral of e to the x squared, we're actually going to see in chapter 11 how to find it. So by the end of this class, you will know how to, like, what the integral of this function is. And it cannot be written using any combinations of functions you've ever seen. It cannot be written using any finite combinations of anything you've seen. And it turns out that the majority of elementary functions don't have elementary antiderivatives, including all of these. And we'll learn how to do some of these in chapter 11 as well. All right. Last thing we want to talk about is how do you study for an exam using this? The other stuff we've learned in this class, you basically were told what technique to use, or the way it looked just told you what technique to use, but that doesn't happen anymore. We're in chapter 7 now. So just understand that on an exam, I'm not going to ask you to just do a bunch of integrals. I might have you just identify the technique to do it, or the form. I might have you set it up and just simplify. I might have you evaluate it and simplify, or some combination of those things. In addition, you will be given a list of new integral formulas and use them to evaluate other integrals. So there's even more to learn in chapter 7. But in terms of like doing the homework and using this homework, this section to study for a test, this is about, can I recognize what technique I'm supposed to use? And then you further want to be able to do the integrals as well, but on a test I might not require that because some of these problems take a long time to do, as you're well aware already by now. All right, well, that's it for this section. If you got any questions, let me know. And I'll see you next video. Bye-bye now.